So if you want to convert from polar coordinates to rectangular Cartesian coordinates, you can see the polar axis is x and that's the y-axis, and we have this connection that x is equal to r cos theta and y is equal to r sin theta, or conversely you can see that r is equal to x square plus y square square root and theta is equal to tan inverse y over x. So if you know the polar values r and theta, you can find x and y. If you know x and y, we can find the polar values. So suppose I know the x coordinate is negative 2, y coordinate is 4. I can find the corresponding polar values. Then r is going to be square root of 20 and theta is going to be 116.5 degrees. Here. I wrote it in degrees. You can also do radians if you want. In the next example, I have polar coordinates r and theta. Here I have written theta in radian. So r is 3. That's the distance from the origin and the angle of pi by 4. So 45 degrees if you want. 45 degree angle. And I can convert it into x and y using my conversion formula. X is equal to 3 cos pi by 4, so 3 root 2, and y is also 3 root 2. So you are in the first quadrant because your angle is only pi by 4, so 45 degrees. So you are in the first quadrant and your answers for x and y. So you should be able to convert from polar coordinates to rectangular Cartesian coordinates and rectangular Cartesian coordinates to polar coordinates using this conversion formula. So let's look at complex numbers in polar coordinates. So let z be x plus iy, and then we can change it and look at them in polar coordinates. So x is equal to r cos theta plus y is equal to r sin theta, and I can factor r out, and I can write that complex number in polar coordinates r cos theta plus I sin theta. We call r the modulus of this complex number and write r to be the absolute value of z, which is of course x square plus y square square rooted. We know that. And theta is called the argument. It's just two names that have appeared in the literature. So using polar coordinates, actually multiplication and division becomes much easier than using rectangular Cartesian coordinates. Suppose you have two complex numbers, z1 and z2. Multiplication actually is very simple. When you multiply these two complex numbers, z1 times z2, the moduli multiply, you have the two moduli multiplying, and the arguments just add. So you just have to multiply the two moduli and add the arguments. So division equally easy. If you want to divide a complex number by another complex number in polar coordinates, you just divide the moduli and subtract the arguments. These are very easy to show. I'm not going to show them, but all you need to do is to multiply these two. If you multiply and use trigonometric compound angle formulas to get this, cos A plus B is cos A cos B minus sin A sin B, etc. The compound angle formulas for trigonometry, you can easily derive these formulas. And division, the same thing. You can get this formula if you just do the division, and then you need to multiply by the complex conjugate, and then again use the compound angle formulas for trigonometry, and you can easily show these results. What's even more useful is if you want to look at for powers. If you want to look for Zn, then it's just the argument raises to the power n, and the angle just gets multiplied by that, because you can see that if you put square, if it is the same, if you want the squaring, then you will get r squared here, and then this will be 2 theta. So if you want the nth power, then it's just the arguments multiply and the moduli multiply and the arguments add, and then that's easy. You can just imagine if you had x plus iy, and if you had to do it to the third power, it's going to be really difficult. Suppose your complex number was 2 plus 3i, and if you want to find the fifth power, then you will have to raise that to the fifth power, and you will have to use maybe binomial expansion, and there will be so many terms, and that will be a lot of work. But if you have it in polar coordinates, we can just use this formula and we have it in standard form in polar coordinates. So for multiplication, division and raising to a power, polar coordinate representation is easier for us to use than the rectangular Cartesian representation of the complex number. We can also write complex numbers in what's called exponential notation. So if z is equal to r cos theta plus I sin theta, then we can write this as r e to the I theta, and we use this identity. There is an identity, e to the I theta is equal to cos theta plus I sin theta. And you can use this identity to rewrite the complex number if I want in exponential form. So technically we can write a complex number in three different forms. We can write in rectangular Cartesian coordinates form, x plus iy. I can write it using polar coordinates, r and theta. or I can write it in exponential form, or e to the I theta, replacing that in exponential form. The exponential equation is a very famous equation. Mathematicians have loved this equation. It was found many years ago. E to the I pi plus 1 is equal to 0. It connects. E to the I pi is cos pi plus I sin pi. Cos pi is negative 1. Sin pi is 0. So this becomes negative 1 plus 1 is 0. Where e is the square root of negative 1 and pi is a famous irrational number 3.1415. So it actually connects I, the imaginary number, pi, the irrational number, and unity, that's 1 and 0. So that's the identity for multiplication, identity for addition, and it's a beautiful equation in mathematics. A polar representation of complex numbers is especially useful when we want to look for the nth root. Unlike in Cartesian coordinate forms, if you want to solve this equation Zn is equal to some a, complex number a, then we can solve this equation, find the roots of this equation from this formula. So Z is equal to the nth root of r and cos theta plus 2k pi over n plus I sin theta plus 2k pi over n, and the n roots are given by these values for k going from 0 up to n minus 1. And so you will note that Zn equals a equation has n solutions in complex numbers. This is called the fundamental theorem of arithmetic. This is true in complex numbers, but in general we know that for real numbers this is not true. In polynomials you will not always get, if your degree 4 doesn't mean that you will have 4 real roots, because some other roots can be complex numbers. Or degree 2, even degree 2, the quadratic equation sometimes, even if it's real number quadratic equation, may not have real number solutions. But in complex numbers that's not the case. In complex numbers, if you have